Good morning. Still, kind of. So as your last presentation before lunch, I just want to bring one simple idea to you. Does this thing work as a laser pointer? How do you make this laser point? Ah, never mind. Okay, sorry, I was hoping to use a pointer. So that idea is that we need to develop a software stack for neuromorphic. And so in the past, we've had a lot of focus on developing hardware for doing neuromorphic computing. And in recent history, there has been an increasing emphasis on the algorithms. And I think that's a good trend. So one of the technologies that, oh, thank you, Murat. I'm afraid it doesn't work for me. What's your magic? We'll skip that. Thank you. So one of the key technologies that enable this in the conventional computing world is the classic software stack. And although this varies from platform to platform, like a Mac is going to be a little bit different than your PC, your Windows system, and someone who knows how to program one has a little bit of a learning curve to program the other. I would argue that the distance between those two is much, much closer than the distance between either of them and programming a neuromorphic system. And in fact, there's precious few people in the world that can successfully program a neuromorphic system. And I would bet that a good percentage of them are sitting here in this room. And so we have the situation where universities can crank out hundreds and thousands of people that know how to program classic machines, and they get sucked up by big internet companies. And we have a handful of people that can program the neuromorphic systems. And so we need to make progress towards the capability of an average person being able to program these. Existing efforts in that are like the gateway system that the European brain community has for accessing Spinnaker and brain scales. I haven't actually used it personally, but I have looked at it, so it's an impressive piece of technology. And another example is Chris Eliasmith's neuroengineering framework. So those are good efforts in that direction. One reason why programming neuromorphic systems is difficult is because they're not a conventional system. And a lot of the pillars that we have under us kind of get knocked out. The job of a compiler and a loader end up having to be done generally by the host system. We don't necessarily have access to hard disks, and a neuromorphic system may not even have a processor in the conventional sense or memory in the conventional sense. C++, Python, all of those languages simply aren't a fit to the systems, and the POSIX standard you can just forget, right? So let's drill down on one notion of one job that a operating system does for us, and that is to provide device drivers. That's to generalize access to a particular class of hardware so you don't have to know the exact details about it. And a suggestion I have on that is that for neuromorphic systems, particularly spiking systems, we could agree on some standards, say, for arrangements of spiking neurons that you would view as an input pattern or for output. So this illustration here talks about a video input, and you could imagine, say you have a 1K by 1K neuron array that would produce spikes that then you would always know, if we had a standard for that, you could write software that would always know that there's going to be that array there. You would know its shape and size and expect to get spikes from it. Similarly, if you were trying to control a robotic platform, you might have, say, 100 neurons that if you deliver some pattern of spikes to them, it'll operate the motors. This is all notional, but I'm suggesting that we could, maybe as a community, discuss creating standards for these so that they fill the role of device drivers. I want to talk briefly about our experience at Sandia developing a software stack for a neuromorphic device we've been working on called the STPU. When we started studying this problem, one of the things we thought about was what, if we were to write once, run anywhere software, what would be the basic interface that we would work towards? And an observation I made was that it seems like almost every neuromorphic hardware, at least spiking systems, tend to have something equivalent to a leaky integrate and fire neuron. They support synaptic connections, which have delay and wait. And so this is actually a fairly simple model. And it also happens to be pretty much a fit for the hardware we were developing, too. I ended up building a software stack for this system that essentially takes this model, these lift neurons and synaptic connections, compiles it for the hardware, and it deals with the I/O issue by separating the neurons into those that can be put on the hardware and those that cannot. Neurons that do I/O happen to be not able to run on the hardware, so they end up being left on the host and where they communicate with files on disk and things like that. And then as many neurons that follow the lift model as possible get pushed onto the hardware. Just to finish up, I want to put one more thought before you, and that is what's our vision of the future of neuromorphic computing? What's it going to look like? Right now, there's kind of three major ways of thinking about neural computing. There's the tensor flow type networks, which is pretty much what deep learning is these days. A lot of support, several different libraries for it. And then we have spiking networks, which are kind of more obscure, more in our community. And then there's neuroscience models where the goal is really more to simulate and understand the actual brain systems. And the question I want to put before you is, where do you think the innovative algorithms are going to come from in the future? I'm of the opinion that they'll be coming from neuroscience. I could be wrong. Sometimes people can come up with stuff just by thinking hard, but I think that understanding the brain is going to help us develop better solutions to actual problems. And what language is best for expressing those? Well, if the algorithms are coming from neuroscience, I suggest that we should be looking for the kind of computation that's typical of neural simulations, which includes dynamical systems and well, those class of the class of math that's used for the neural simulations. And I want to put in a plug for my poster and demo later. I've been working on a tool that does this kind of modeling, and if you'd like to have a look at it, I'd appreciate you coming by.